Okay, I'm going to get started here. It's 10:45, so good morning, everybody. Thank you so much for being here. I realize it is a rainy day on the last day. It's snowing, last time block for the RIC, so thank you for being here again. Your commitment to nuclear safety is real, so I commend you. So we are at a remarkable moment in nuclear energy. Across industry, government, and research institutions, we're seeing an unprecedented wave of advanced reactors, new fuels, new applications, and entirely new ways of thinking about how nuclear technology integrates into our energy system. Across all areas, we're thinking about how innovation requires us to think about some critical questions. How do we ensure that safety, reliability, and public confidence can move forward just as quickly as the demand for the technology itself? That's where advanced enabling technologies comes in. Today, we're not just talking about new reactors, we're talking about tools for understanding, operating, and regulating them. Tools that allow us to see deeper into systems, predict performance earlier, detect degradation sooner, and make smarter decisions faster. Technologies like high-fidelity modeling and simulation, digital twins that replicate reactor behavior in real time, advanced non-destructive examination techniques, continuous condition monitoring and passive mechanical components, remote and autonomous operations, and the cybersecurity frameworks needed to protect increasingly digital systems. These technologies are not science fiction anymore. Many are already transforming industries like aerospace, manufacturing, and medicine. The opportunity before us is clear. How do we harness these tools to strengthen nuclear safety and enable innovation at the same time? That challenge has also been recognized at a national level. The recent Executive Order 14300 calls for the use of emerging technologies to safely accelerate modeling, simulation, testing, and approval of new reactor designs. In other words, the moment calls for us to rethink not just what technologies we build, but how we evaluate, monitor, and regulate them. For decades, nuclear safety has been built on rigorous engineering, strong regulatory frameworks, and deep technical expertise. Advanced enabling technologies offer the chance to extend those strengths, to reduce uncertainty, detect problems earlier, improve operational insight, and make safety margins more visible and measurable. But realizing that promise requires collaboration. It requires industry innovators, researchers, regulators, and technology developers to work together to answer key questions. Where can these technologies provide the greatest safety value? How do we demonstrate their reliability for safety-related applications? And how can we incorporate them into regulatory frameworks without compromising the rigor that nuclear safety demands? That's exactly what today's session is about. This discussion is an opportunity to explore how advanced and mature technologies can transition from promising tools to trusted components of the nuclear safety ecosystem. Because if we get this right, the payoff is enormous. A future where our nuclear fleet is not only innovative, but measurably safer, more observable, and more resilient than ever before. And a future where technologies we develop today can help ensure nuclear energy continues to provide clean, reliable, and safe power for generations to come. I'm excited to hear the perspectives from our speakers and from all of you as we explore how to turn these possibilities into reality. I'll get started with a couple of quick introductions for each of our presenters. First, we have Dr. Raj Iyengar. Dr. Iyengar leads the Research Reactor Engineering Branch in the Division of Engineering in the Office of Nuclear Office of Nuclear Regulatory Research. During his NRC tenure, he has been building and nurturing effective partnerships with internal teams and external organizations to align regulatory research with future industry needs. Dr. Iyengar has authored and co-authored over 70 publications focused on emerging technologies, including advanced materials, modeling and simulation, AI applications, and nuclear spent fuel storage and next-generation reactor components. Raj holds a PhD in solid mechanics and a master's in applied mathematics from Brown University, and also a master's in mechanics and material science from Rutgers University, and a master's of meteorology from Indian Institute of Science. Next, we have Ms. Cheryl Gayhart. Ms. Gayhart is the Vice President of Regulatory Affairs at Southern Nuclear Company. Cheryl assumed her role in 2024 at Southern Company after serving as the site vice president since 2013 and plant manager at Farley Nuclear Plant, where she was responsible for overall safe operation and maintenance of the plant. She has also previously worked in roles in increasing responsibility at Braidwood and Byron Station. Ms. Gayhart graduated with a bachelor's degree in mechanical engineering from the University of Illinois at Chicago. Next, we have Mr. Taylor Smith. Mr. Smith is the Director of Special Projects for Vistra's nuclear fleet, with coming on 18 years of nuclear experience spanning engineering, maintenance, licensing, major projects, and innovation. He leads fleet-wide initiatives in license renewal, power uprates, and AI integration, driving projects that optimize performance and keep nuclear generation competitive in today's energy landscape. We also have with us today Dr. Ellen Serretta. Dr. Serretta is the Associate Laboratory Director for Physical Sciences at Los Alamos National Laboratory, where she oversees material science, manufacturing, experimental physics, and accelerator science capabilities, foundation to the nation's security and energy security missions. An internationally recognized materials scientist, her research links microstructure to dynamic material behavior and impacts across shock physics, explosives science, and performance-critical materials. Prior to becoming ALDPS, she led the Materials Science and Technology Division and held senior positions advancing manufacturing science, energetic materials, additive processes, isotope production, and prototype fabrication, with a strong emphasis on data-informed design and accelerated technology maturation. Dr. Serretta earned her PhD and master's in materials science and engineering from Carnegie Mellon. She also holds a Bachelor's of Science in Aerospace Engineering from the University of Virginia and is a fellow of the ASM International and served as the 2021 president of the Minerals, Metals, and Materials Society. We also have with us today Mr. John Nikoski. Mr. Nikoski is currently the Deputy Head of Regulation for the Division of Nuclear Safety Technology and Regulation at the Nuclear Energy Agency of the Organization of Economic Cooperation and Development. He has more than 40 years of experience working in the nuclear industry, mostly as an inspector and regulator here at NRC. He has held leadership positions at NRC in the areas of operating reactor licensing, project management, pressurized water reactor systems, rulemaking, license renewal, operating reactor and construction inspection program development, quality assurance and vendor oversight, and probabilistic risk assessment development and application and regulatory decision-making. In addition to his background at NRC, Mr. Nikoski has worked at NEA between 2010 and 2013, where he provided technical support to countries embarking on nuclear power programs and supported NEA's efforts in response to the accident at the Fukushima Daiichi nuclear power plant. Prior to working at the NRC, he was a nuclear test and refueling engineer for the U.S. Department of Navy at Puget Sound Naval Shipyard. Lastly, and most importantly, I would like to also recognize Mauricio Gutierrez and Doris Lewis, who are the coordinators of this session and whose hard work made this session possible. So if you would, just please join me in giving them a quick pause of recognition. And with that, I'm going to turn it over to Raj.
Thank you so much, Caroline. It's a great privilege to stand in front of you to highlight how our staff is enabling the safe and responsible use of enabling technologies for a safer nuclear future. I want to start with a few. Some of my comments will probably resonate or reinforce what Caroline said, so forgive, we didn't talk to each other, but that's how we think. So I want to start with a few quick thanks. Mauricio Gutierrez for his incredible work in coordinating the session, AJ Sherman and Chris Nellis for building this presentation, and to many staff members whose input made this possible. I also want to recognize the support and encouragement of our Division Director, Christian Araguas. This session was his vision, and we are proud to bring it to you today. You likely noticed a swan in my opening slide. You may wonder why. Ancient Indian scriptures mention a mystical swan that has a unique ability to extract pure nectar from water. That's exactly how our researchers operate. They sift through complex scientific data, operational experience, and expert insights to extract only the core insights that matter for safety and risk. The rest, no matter how interesting, does not distract us from our mission. Enabling technologies are the catalyst for advanced nuclear energy and the innovations in these new nuclear technologies. They aren't just facility designs, they are commercially viable breakthroughs in fuels, materials, sensors, digital systems, and advanced modeling and simulation. And of course, I have to mention AI and machine learning. I think everybody is so interested in that. These technologies could be deployed to improve performance, speed the deployment, lower cost, and strengthen safety. Because these technologies have a direct nexus to safety and risk, we have proactively evaluated their adoption. We strive towards the development of technical bases, assessment tools, and guidance that are necessary to ensure efficient licensing within our flexible regulatory framework. In the following slides, I'll highlight our key accomplishments in this area. Throughout the effort, we remain laser-focused on one thing: impact-driven outcomes. Finally, I want to recognize the extensive expertise and support we've received from our partners from the DOE National Laboratories and the National Institute of Science and Technology. Their partnership and contributions have been invaluable and essential. Material selection and qualification for advanced reactor designs are long lead and design limiting challenges. Furthermore, the complex components required for these systems necessitate the use of advanced manufacturing technologies. Our systemic approach to evaluating safety and risk of these technologies began with the agency's 2017 Vision and Strategy document and the Implementation Action Plan for licensing non-light water reactors. Since then, we have made significant progress in expanding our technical bases, formulating guidance necessary for a stable regulatory environment. Most notably, we have achieved pivotal endorsement of codes and standards for high-temperature construction and reliability and integrity management. These, along with the evaluation tools we have developed, provide the necessary framework to support efficient, safety-focused licensing. I want to specifically recognize the technical support and expertise from Argonne, Idaho National Lab, Oak Ridge National Lab, and Pacific Northwest Lab in achieving these milestones. Next, our safety codes, which were developed for 30 years ago, was largely focused with light water reactors. Of course, with the invent of new advanced nuclear technologies and advanced non-light water reactors, they needed a reboot. And to support the licensing of these reactors, we have pivoted our research toward enhancing our safety code capabilities, specifically adding plant and multi-physics models for fast reactors, high-temperature gas reactors, molten salt, and microreactors. Through close coordination with DOE's Nuclear Energy Advanced Modeling and Simulation, also known as NEAMS program, as well as with Idaho National Lab and Argonne, we have developed the Blue Crab suite of codes. This suite represents a globally significant advancement in our ability to evaluate advanced reactor designs and operations through a scientifically rigorous, risk-informed lens. Blue Crab has already proven essential in supporting our licensing reviews and has become a priority resource to our external stakeholders seeking predictable regulatory path. Recent advancements in Sandia National Lab have provided us with sophisticated government-sponsored modeling and simulation tools for physical security. These capabilities include path analysis, tabletop visualization, high-fidelity combat simulation. We have evaluated these modeling tools for applicability within our regulatory framework. And may I have our staff to present you with what they're thinking. Can you play the physical security video, please?
Physical protection is important for the secure use of radioactive materials. This is a complex challenge, as security analyses require not only the consideration of actions by licensee personnel, but also by adversaries who are deliberately trying to figure out ways to avoid or defeat the physical protection system, which is a complex combination of equipment and responders devoted to protecting nuclear facilities from malicious acts. With advances in computing capabilities, the nuclear industry is beginning to use innovative modeling and simulation to accomplish many steps within the vulnerability assessment process. The NRC is working to assess the technical considerations of computer modeling to inform regulatory guidance development and support efficient evaluation of licensing actions that make use of these innovative technologies.
Thank you. The next topic is something that most people are not aware of: materials control and accounting. These programs are well established for current fast light water reactors. However, unique fuel forms in advanced designs, particularly liquid fuels, offer new challenges for tracking and verifying special nuclear material. To address these complexities, we have been collaborating with experts from Los Alamos National Lab to utilize advanced modeling and simulation. This allows us to identify best practices for MCNA in a way that's both cost-effective and strictly risk-informed. A key area of our focus is liquid fuel molten salt reactor. Because the fuel is integrated with the coolant, traditional measurement techniques may not be sufficient. We have proactively outline potential technologies and approaches that applicants can utilize to meet MCNA requirements in these complex environments. The next topic is something that we leaned a little bit too far, way forward 6 years ago, because we had a little bit of seed money on a future-focused research program. We initiated some activity on digital twin technologies and technical and regulatory considerations. At the same time, DOE, ARPA-E invested several orders of magnitude more funding to look at the commercial viability and technical utility of these technologies. At the time, this was largely conceptual. People raised eyebrows when you mentioned digital twins. But everything changed the last 2.5 years. You know why? Because the advent of AI and machine learning and exponential rise in these various algorithms have made some of these digital twins techniques possible. I understand that a couple of advanced reactor vendors have been working on developing digital twins for their systems, as well as, I believe, one fusion potential licensee is also looking at using digital twins for their facility. Now, again, our staff is better to talk to you about digital twins than I am. Can you please play the video for digital twins?
Digital twins are an innovative technology that draws upon data from the real world to create virtual replicas of physical assets, which may allow engineers to simulate and analyze every aspect of a nuclear plant's operation in real time to identify and resolve potential issues and enhance safety and security. Such as operator training, safeguards and security, and facility construction and inspection. One near-term application that is being focused on is the use of digital twins for condition monitoring and anomaly detection of mechanical systems. Further exploration of this potential use case was achieved using a boiling water reactor plant simulator as a surrogate for a physical plant. Staff used the simulator to gather realistic plant data representing normal states and faulted states of a safety-related system. This data was used to train and test machine learning models that were able to provide early detection and classification of faulted system states. Innovative digital twin technology has the potential to revolutionize how we design, operate, and maintain nuclear facilities.
Thank you. Well, you're going to hear a lot about AI and machine learning from the other speakers. I wanted to give you also a flavor of what we are doing, a couple of new things that we are working on in terms of application of machine learning for engineering purposes. The first example is the one that deals with the application of machine learning for non-destructive evaluation, where we can potentially minimize the burden on humans to do these UT reviews of, of NDE to see if there are flaws or not. We are partnering with PNNL and Oak Ridge to develop technical bases and guidelines for AI-enabled NDE. This work supports predictable regulatory decision-making by establishing best practice guidelines for assisted flaw detection in manual and encoded inspections, the use of synthetic data for training both personnel and algorithms, data set qualification, including distribution and uncertainties. Our staff is evaluating both supervised and unsupervised machine learning algorithms. Supervised machine learning algorithms could use either a binary or classification, the one shown in the picture here, or anomaly detection, which is not shown here. Unsupervised learning methods involving principal component analysis and clustering are also effective. And our work shows that the unsupervised machine learning methods are pretty effective if you used them properly. The next example is another thing that we're working on. You heard one of our staff in the video talking about applications of the machine learning for condition monitoring. So when that's going to happen, we as a regulator need to evaluate the safe use of these kind of technologies and to identify guardrails. To that end, we are working with Argonne National Lab to develop technical bases to ensure machine learning applications for nuclear power plant components. I understand there's lots of activity going on in enhanced monitoring and diagnostic center for current and new operating fleet, so I think these kind of technologies would be very, very useful. So in order to achieve this, we have established a framework of regulatory guardrails across 4 critical areas you see in the picture here. Model development and validation, ensuring the foundation of the AI is technically sound. State assessment, accurately interpreting the current condition of the system and using that information to do prognostics, predicting future states and potentially failure points. And then, of course, we have to have human in the loop to make sure the decisions are made appropriately using the recommendations from the machine learning algorithms. Now, these guardrails are essential for safety-critical systems, as you all know. But I will also point out these guardrails are also important for non-safety components because they avoid a lot of unnecessary repair and replacement due to faulty predictions. So it is something that all of us, whether we are a regulator, whether you're a licensee, we all need to be interested in appropriate application of these technologies. I have only a couple of more slides, I think. The last one is not my area. So finally, we are evolving our approach to digital systems and wireless security to match the complexity of modern designs. Current safety evaluations are often challenged by deep interdependencies in digital systems. To address this, we are developing technical criteria to support risk-informed performance-based reviews of digital INC systems. By leveraging modern hazard analysis techniques and organizing evidence through safety assurance cases, we aim to reduce review time and regulatory uncertainty while maintaining rigorous safety standards. As the industry adopts wireless technology for equipment monitoring, including safety-related and important safety functions, we need to address unique cybersecurity challenges. We recently released a report documenting our research in potential cyber vulnerabilities. This provides the technical basis for evaluating wireless implementation, ensuring the introduction of these technologies does not compromise the safe security of critical digital assets used for monitoring. Our goal is simple: to ensure that as the industry innovates, our regulatory framework provides a safe, secure, and efficient path forward. I think I'm coming to my last slide. So in summary, we've highlighted how enabling technologies can transform our industry and our regulatory reviews and our fundamental responsibility to ensure their safety applications. By being proactive and prepared, we are paving flexible and practical pathways for adoption of these technologies within our regulatory framework. In closing, I want to acknowledge the magnitude of this moment. We are standing at the crossroads of unprecedented innovation, urgent energy transformation, and historic investment. While our individual roles and mandates are distinct, we share a collective responsibility to converse, collaborate, and deliver a safer nuclear future. That work starts here, and it starts now. Thank you so much.
Good morning. Good morning. As Caroline said, I'm Cheryl Gayhart. I'm the Vice President of Regulatory Affairs at Southern Nuclear. Southern Nuclear is the proud operator of the two newest reactors in the United States, Vogtle Units 3 and 4, along with our other plants, Vogtle Unit 1 and 2, Hatch Units 1 and 2, and Farley Units 1 and 2. For centuries, our most powerful tools have been words, procedures, policies, and expert judgment. Today, artificial intelligence allows us to translate those words into useful tools and numbers. That shift from words to tools and numbers matters everywhere, but nowhere more than in the nuclear industry. By turning operational knowledge and real-time data into predictive insights, AI can help us detect risks earlier, support better decisions, and strengthen safety without replacing human expertise and our approved NRC methodologies. In an industry where safety is paramount, AI becomes not a substitute for judgment, but a powerful reinforcement of it. So let's start talking about the words. AI is evolving at an extraordinary pace, faster than our policies, budgets, and comfort levels. We face real constraints, limited resources, competing priorities, and a natural fear of failure when adapting new technologies. But standing still carries its own risk. The challenge before us is not to use AI perfectly, but to use it responsibly, learning, adapting, and improving as the technology itself continues to change. Every decision we make is based on what's best for our customers, and nuclear has a very important role in keeping our lights on. And the more we can do to enhance our processes within our fleets, and the more value our owner companies can pass on to our customers. Sorry. So our AI journey matters even when projects don't make it into production. Simply learning how AI works opens doors and changes how we think about problems. An AI agent or a tool isn't about making decisions for us. It's a knowledge base that helps us be better at our jobs. That's why at Southern Nuclear, we've built a fleet AI working group with every department and site involved, supported by communications, training, and cybersecurity. In 2025 alone, this group delivered over 50+ training sessions fleet-wide for our employees, and in 2026, we're going to continue to deliver quality quarterly training. Our AI developers are not IT or AI specialists, but our workforce that has embraced the use of this new technology. When AI moves together with the business, we create solutions we can actually use to make our business more efficient and reliable. So this is our AI strategy, and it's working because we have one that is robust. Every initiative we pursue is mapped directly to our business strategy to focus on solving real-life problems that improve performance, reliability, and efficiency. We rely on our citizen developers, which are really just our employees, and an active AI working group to move forward while empowering those employees at the grassroots level through safe tools like Copilot, training, and conducting lunch and learns. Leaders at all levels foster a culture where team members are encouraged to share innovative ideas and solutions, shining a light on ideas to develop and create a safe space for experimentation. And importantly, we don't go all in on a single vendor. We combine diverse partners with in-house and industry developers to solve real problems, business problems the right way. Our AI strategic goals for this year will focus on continued AI literacy and adoption, adding more users and agents, and requiring the use of selected AI tools as part of our workflow. So along the way, we've faced some challenges. First impressions weren't all that great, so we had to re-engage and bring people back in. Taking baby steps to allow people to explore and to use AI for simple things such as email sorting and presentations allows them to be more comfortable when more complicated problems are being solved with AI. And there's also choice overload, so many possible uses that it can feel overwhelming. Many of us don't realize how much data they already have, how we have access to, and without measuring usage, it's hard to know what's truly working. And add to that our nuclear DNA. We are trained to get it right the first time, so the stakes feel really high. That's why data security is critical. We use approved tools with security built in so people can explore and learn with confidence. At Southern Nuclear, we have deployed over 70+ co-pilot agents for our fleet to help our workforce solve problems, be more efficient, and it allows them to do the work necessary to keep our units running safely and reliably. AI agent applications run from corporate functions like communications and human performance to technical roles like engineering, operations, and licensing. While we have deployed many agents, I will only touch on a few to give you an idea of how these agents are specifically stand out to support our plant maintenance and operations teams. For example, we have a safety observation agent that enables a supervisor to verbally use their phones, document observations, and AI does the work of categorizing those observations and enters them into our safety database. Our internal operating experience database allows anyone to search for a previous issue and learning and to allow our workforce to use those learnings as they prepare to do tasks in our plant. Our organizational performance, effectiveness, and performance improvement agent is instrumental in fostering high-quality improvement plans for our departments. By assisting in the development of improvement plans and communicating underlying issues, this agent is used to create improvement plans to advance precision, craftsmanship, and overall maintenance effectiveness at Southern Nuclear. And lastly, as you know, our summer and winter readiness performance is key for our nuclear plants. And we have a summer and winter readiness classification model that was built to review and classify work tickets that allow us to ensure the right maintenance is done at the right time prior to those peak periods. This model was reviewed and was 98% accurate in predicting the work orders that were needed to be done. This agent alone, used and predicted, resulted in hours where it would have taken our employees weeks to do that work. AI has simply knocked it out of the park in how we use it and how it's useful in our day-to-day jobs. Since we just heard about how AI is changing our future, especially with large language models for the agents we discussed, let's look at a different but unique application of AI called machine learning. In the last few years, Southern Nuclear has been exploring ways to reduce our end-of-cycle D rates at plant hatch based on moisture carryover, or MCO as it is shown on the slides. Moisture carryover is the amount of liquid water mixed with steam leaving a boiling water reactor. There are design specifications limiting how much moisture carryover is permissible before the operators must take remedial actions, of which one of the options is a costly power D rate. Up until recently, there has been no reliable, easy method to forecast future moisture carryover levels prior to or during a new fuel cycle. Consequently, the primary method to mitigate high moisture carryover is to design the core with a larger than required batch size, thereby increasing potentially unnecessary high fuel reload costs. This grassroots effort to better predict moisture carryover started with a company called Blue Wave. And Blue Wave started out with professors and grad students and has grown based on the use of this technology. Moisture carryover prediction was a problem, a very complex problem, and the technology was able to produce solutions to this prediction better than the use of a traditional complex physics problem. This blue wave technology allowed us to use machine learning for these predictions with a solid confidence in the data predictions. This technology used AI coupled with machine learning to leverage historical fuel cycle data, outputs from core simulators, and past moisture carryover measurements. It is important to note that this predictive technology is a tool and does not take the place of our NRC-approved methodologies. So it's important, you can't press the I believe button here. Just like large language models, you need to understand the boundaries for what your data is telling you. We have only scratched the surface with these tools, so now let's see how these predictions measured up. So here's a great example of how the machine learning prediction measures up against actual plant data. The black dots you see on the curve are actual plant performance. The light and dark green lines are machine learning prediction. So this graph shows exactly how accurate this prediction is. The use of these predictions allowed our fuel engineers to understand where moisture carryover will impact our power levels, and thus they were able to minimize the operational impacts due to generation, as well as keep our fuel costs low. This figure shows how intentional we are with each AI use case and how much fidelity we expect from the tool. We build confidence by clearly defining boundaries because with machine learning, again, you can't press that I believe button. This graph highlights the relationship between potential failure and model autonomy, and we deliberately operate in the lower left-hand quadrant. Above all, a strong collaboration with utilities and AI vendors through validation and continuous learning has enabled the predictions to be far beyond what we could ever achieve by hand. So thank you for your time today. By the way, I wrote this presentation with AI, and all my notes came from AI, but I did a good review. Thank you.
Good afternoon. We're right at the end. Everyone's kind of sitting in here, and we're like, all right, the last session, last day, everybody's hoarse from talking all week, and it's been a long deal. And what I'm going to share here is a little bit of the situation of how all this stuff is mature enough to actually be developed into things that help nuclear safety, helps the operators. And I'll give a lot of credit to the NRC, is they're reaching out to the industry for ideas and growth and people that are doing it and how we can transform and work together, because we absolutely have that mission in mind. And in this, I will ask, there's a few people in the audience that know me that I need a squirrel catcher. So I'll get over here on the right and I'll get going. Somebody yells squirrel and I'll get back on topic. But when I was working on this, my dad called me and he heard about this and he's like, hey, I'm calling you and say we're real proud of you. And I realized, so he's a cowboy in New Mexico, and I was trying to explain to him what I'm doing, and it was a world too far away. And I realized how transformational that I'm trying to explain what we're doing today, and we're living in a generation that is going to transfer how we do this. And a key popped up when they talked about the nuclear DNA. And if I was going to draw nuclear DNA, it would be stacks of paperwork in a spiral, right? That's what makes up a plant. Like that's, people that really know it's fatal flaws, there's a calculation somewhere, those are the things that they really worry about, the details. And what makes us special forever was how hard it was to do all the paperwork, right? Difference between us. And what we found now is that's what makes us special, to be able to operate at a whole different level. And what I'm going to show here is a project that we started with our nuclear DNA. And what I did is I started with a feed pump. And why? Because if you make steam, you have this. It's relatable. It's also the attributes of it. It's easy to validate. And as an operator, it costs 70% of all trips. So if I'm going to study something and create something, let's start with something that has the biggest impact to us. That's challenging reactor safety, right? Every time I challenge that, that is absolutely something I want to avoid. So what data do we have that's validated? When you go and you look at nuclear data, every bit of work order had the foreman check that is complete. There was all your evals. They break into manager reviews. And so when people pull nuclear documentation, They know it's the truth. Now we have access to that truth at a level that we've never seen. So we started thinking, like, how can we plug this together, and what data do we have that we absolutely trust? And so what that turned into, if you look here, so we run Maximo, so I have all the data in the tables, and those are design control fields. We trust those. We have oil analysis, gives us real-time wearing stuff. We have vibration. How are you doing today? You know, we have our cap data. What did we do last time we did that? What is the corrective action? If you've ever worked at a power plant and something happened, there's a good chance that is not the first time that's ever happened, right? You just can't find it. You know, we have narrative logs. What is the operators doing? When something popped up, somebody just touched it, right? Somebody just worked on it, or the most probable thing, so we have that available. Now we have Pi data, or, you know, M&D Center, whatever you're doing, we use Pi. So as we die that, what do they all have in common? They have little t, right? They have timestamps. Every work order, everything has an equipment group. Everything's tied to something with time. Now I can lay over how you're actually doing, what you did last time this trended, and how this works. So with that, so this is kind of an explanation of what we're on a dashboard. So this is a feed pump. Comanche Peak, it's yellow, I have an issue. Oh, let's double click there. I got feed water. Let's go a little deeper. Now I got a feed pump issue. So what am I having here that I'm actually looking at this issue, and it's gonna give me the Pi data with the recent things that are relevant tied to that equipment group. All this is pulled together. We already know all the sensors that are tied to this. It's in the design basis document. It's in your procedure. So they're already grouped together, and AI can find those and pull those stuff together. So I'm laying over the whole picture. And so the challenge, and I was talking to the NRC, we kind of just ad hoc kind of heard something, started conversations, is how does this help the future of this? Is, well, you can find trends as you pull this picture together that you've never been able to find, that can see small degradation, something that has aging factors, or something that we've never been able to use and bring to the surface fast to run us safer, right? So how are we using enabling technologies to be safer, and how do we design our plants in the future? And I'm even thinking this through our uprates. So Vistra's doing a number of uprates we've made public. You know, we got Perry, Davis, Bessie, Beaver Valley. How can I instrument this stuff better so I can run this more reliable and safer in the future, right? These sort of things. How can I put these sensors out there? And what it is, and what I'm wanting to show here is the technology is mature. We have language models that can understand all the structured data. We also have the Pi data that we have 20 years of trends, and we know exactly how this thing is supposed to act. We have trigger values in there. We have every bit of data that the ops rounds, and they keep all that put together. So we're finally mature enough to bring this all together with one large picture and bring this as we can really say, hey, how are you doing? Like, feed pump, what are you doing? And they're like, hey, I've been pretty fine. I have an elevated temperature. The last 20 times this has happened, we've had to go balance a lube oil cooler. That's been the ops rounds. I'd recommend that. Okay. We have a licensed operator who goes, I agree with that. Let's go make that. And he goes, oh, by the way, there's a precaution. That lube oil cooler, you better turn that valve only a 1/16 of a turn per 30 minutes because it takes a while to balance. Got it. Check. All safer because of this data, and it is mature enough to actually be real. So this is the transformational part that, like, we don't really see. And what I want to get into here is, I'm really not talking to the slides, right? But I wanted to show you, and as you read here, and these professionals that absolutely can relate more than my dad, that this is not a future, this is not a can be, this is not research. When you look at this, this is real data, making a real analysis of real things that is really available to us. So where we're at in this project, we ran this, we pulled all the data, ran it through events that I have scars from, that I could validate, say, yeah, that happened right, and you would analyze that right. So we're working through that data, and it's good, and now we're plugging it with live data, and now it starts rolling this, and now we start rolling live. And then it's the bigger picture, it's what next, right? How can this help all of us? How can this help the regulator? How can it help the operators? How can it help the safety? How does it help us rethink about the business models of instrumenting our plants? And we're thinking even beyond that, like, how does this look when we look at, you know, like our simulators, right? So now we have all this situation and how this plugs in and what we can do with it, but it's it is all mature. All we're doing is marrying it all together, but it's really the nuclear DNA that we started with that had the, I'm going to say, correct documentation, the perfect documentation. Maybe not perfect, some of it was handwriting. But so now OCR can read handwriting, right? I'm pulling in old work orders that are scanned in, and I can read handwriting and understand that they found some corrosion in this back in, they recoded this, or the coating started to flake or blister or bubble, or all these things that are trends that is also helping even the regulator have access to this quicker, which helps us all when we're in inspections and audits and all this stuff. So all this being available, like, there is not a downside to safety, efficiencies, operations, and it's going to change the power industry. And I mean, it's even the change power industry period, because if you think here, everything I'm doing here is not nuclear specific, right? So this is generation agnostic. So as we're going there, Vistra, we have a large fossil fleet as well. So all this helps all the generation model as our growth, and like we can better utilize our assets. So that's kind of how that, there's a lot going on. I didn't get too squirreled, but I wanted to really show like where we're going with the data, how we're using it. And for so many times in my career, like when I first started on Lotus Notes, I was thinking, why am I writing this much? Like, what am I doing? Like, what is the purpose of this? No one is ever going to read this, right? This failure analysis that nobody's ever going to read, like, where is this going? And it is absolute data gold. That what makes us special, nobody else, maybe the aviation industry, has that much validated data that you can say is truth, that you can actually make decisions on. And as we roll through this, I'll get a little bit more detail, because this is a crew that I would say that absolutely likes detail, right? Is what does that look like when we use it? And I ask it something and it gives me an answer. Well, where did I get it from? It's going to throw the PDFs on the right side when I go context. Oh, that blister. Oh, yeah, that is in the CCW heat exchanger. And I look at that. I just validated that what it gave me, and I have that, was true. And it would have taken me 2 hours to go pull that document. And I'm 30 seconds in. And I said, absolutely, I can sign that. And thank you for this draft. So it's kind of what I have of where we're going, what future are, and how we're kind of working all together. But I definitely thank you for this opportunity and the opportunity to share. And I am excited about it. I don't know if you guys get this feeling, but it's real. So thank you.
Good morning. My name is Ellen Soretta, and I'm from Los Alamos National Lab. I'm really excited to be here. This is a pretty different audience than I typically speak to, and I want to thank you for that kind introduction this morning. Before I get started, I want to make sort of 2 points up front. So just in case I don't get through everything, at least those points are made. Despite the title of my first slide here, the point I really do want to make is that not just Los Alamos or the Applied Energy Labs, but holistically, the Department of Energy national labs have a broad set of capabilities that can be brought to bear to do some of the very things that I believe that this conference is examining with regard to really accelerating new technologies for insertion and advancement of nuclear energy in the United States. The second, and so while I will do that with Los Alamos bent, really highlighting some examples of how capabilities at Los Alamos can be brought to bear to do that, I will try to make ties to places where that's true universally at the labs, plants, and sites in the DOE complex. The second is that I am aware that I'm presenting to you from a nuclear weapons lab, and that seems a bit odd, and that we do have a day job, and I'm sure that most of you have seen the movie. I have situational awareness of the content of that movie. A fact that sometimes isn't as obvious to folks who don't know the NNSA labs maybe as well as I do is that all of the NNSA labs are called upon for a 3-pronged mission. The first is the deterrence mission that you know quite well and we're famous for. But the second is because of the capabilities that we have at our facilities for the deterrence mission, we're called upon to respond to global security issues as well as energy security issues. And some of the speakers on this panel have already alluded to those things, as well as some of the speakers I saw this morning. And so I'm hoping I can make that tie pretty quickly. So the first place I'll start is with that history at Los Alamos. Very, very early on in the inception of the laboratory, which is now over 80 years old, we had a need to understand nuclear reaction history and nuclear fission concepts, and we did that through the design of reactor technologies. Some of that was fueled by an idea that perhaps nuclear weapons weren't going to be a long-lived thing. Turned out that was probably not a right assessment, but nonetheless, the technology that came out of using these platforms to understand the physics of fission better was something that was also long-lived. That was a fairly exciting time in the advent of using reactors to generate energy to put on the grid. And the reason I bring it up is not just to say that maybe Los Alamos has some standing in this discussion, but it reminds me of sort of the time that we're in now, where we're now at a new renaissance of looking at next generation technologies to put energy on the grid, the real return to the need for reactor technologies. One of the things that we're seeing, and we hear loud and clear at the labs, I'm sure many of you hear it loud and clear in the facilities that you're in, is the need to go fast. And DOE leadership has really been clear in the message that not only do we need to go fast, but the U.S. investment in the labs, plants, and sites, particularly within the DOE complex, should be brought to bear to address these issues, particularly in reactor technologies. I bring up the quote from Brandon Williams because he may not have been the first leader in the DOE complex that you would have assumed would have vocalized that point, and yet he did. And this is the quote directly from him with regard to using the capabilities at the national labs for exactly the problems you're trying to address. So let's talk a little bit about what those capabilities are and how we think about them. It could be trite to say nuclear weapons, they're for nuclear energy, and yet there is something to that. I would assert that all the DOE national labs have a mission in the space of taking perfectly good materials and showing that they can be inserted into both existing and novel, high-consequence, extreme environments. This is our job. Whether you're an accelerator lab, an energy lab, or a weapons lab, this is what you do. At Los Alamos, specifically, there's a capability that has a lot of overlay with regard to fission science for obvious reasons. I tend to think about that mostly in terms of experimental capabilities. You're seeing quite a bit of that here on this slide, but I'd be remiss if I ignored our modeling and simulation capabilities, which is another hallmark of a DOE laboratory, particularly in the weapons areas where we can't test our final product any longer. At Los Alamos, we have begun to look at this with regard to inserting new weapons in harsh, high-consequence applications at a rapid rate with sort of a two-pronged strategy. The first is design to manufacture. Let's think about how we design, on paper, new concepts where we get away from really hard-to-make products and impossible supply chains. And the second is prototype to manufacture. When you go to prototype a paper design, let's really be deterministic about which designs are designs where we only intend to make a few of these. And it's okay if when I prototype them, I'm using technologies or manufacturing techniques that really can't be recreated at the commercial scale yet, as opposed to technologies where I'm going to make hundreds, thousands of a part or a component. And I am going to want to translate that to a commercial production place, where so now I need to prototype with manufacturing capabilities that are immediately translatable so that I can get this to market fast. And I'll show you, and while that's a sort of a strange thing to talk about in terms of weapon technology, I'll show you some of the examples about how we're thinking about it in nuclear energy. Because I was afraid that I'd get too excited about the experimental concepts, because I'm an experimentalist at heart, I chose to start with the modeling and simulation capabilities that we have across the complex. Speaker in the previous session, Nathan Capps, talked quite a bit about the NEAMS program, and I most certainly stole this slide from the National Technical Director for the NEAMS program, David Anderson, who sits at Los Alamos, by the way, to show how we stitched together broad programs across industry and the federal government funding agencies to really develop models and codes that can be useful for accelerating insertion of new technologies. A strategy that we're using on rinse and repeat, both at Los Alamos as well as at Idaho, Oak Ridge, other laboratories, is to start with the fundamental physics of the way in which materials are behaving. Specifically in this slide, we're really looking at the fundamental reactions of radiation and matter and how they evolve fission gases at the atomistic and mesoscale levels, incorporating that then into simulations that allow us to really understand the aging of new materials. And that's what this simulation is showing on this slide. By doing this now, we can show the efficacy of these kinds of advanced simulations, these more applied simulations, with that physics basis, that real fundamental understanding of radiation and matter, to insert in technologies that perhaps the NRC and others are using to validate the insertion of new materials. This is how we do it across the board, no matter your harsh high consequence application. Today, we are working with an industry working group that is really looking at accelerated fuel qualification specifically. This is a long-standing capability that Los Alamos has been really committed to with regard to the development of next-generation nuclear fuels. We do this across a broad set of partners. I'm sure I haven't captured all of them along the bottom of the slide. But again, with regard to the development of those models and simulation tools that rely on data that isn't hard to get, data that can be done with separate effects testing, quick tests, agile tests that advance the simulations and the models to the point where you can rely on them with very, very few expensive integrated tests. And this is something that we are deeply committed to. In fact, we've used our own personal funds and investments internally to Los Alamos to examine this problem. Other capabilities go beyond the modeling and simulation capabilities. Like I said before, the laboratories, because of our, at least the weapons laboratories, because of our primary missions, are committed to facilities that can be brought to bear to solve some of the problems being discussed in this room. One of the things that we're quite good at and have a long-standing history in at Los Alamos is pilot-scale production. This gets to that prototype to manufacture strategy that I'm talking about. Is how do we look at not just making a small amount of a novel material and saying, gee whiz, I hope you can make a lot of it some other way, but really think about, I made a small amount of the material, and now if we're going to make a large amount of this material, I can show you how to do that with the production techniques that you have on your plant floor so that I can go from a few grams to hundreds of kgs to thousands of kgs. And while at the lab, we're not going to do that thousands of kgs issue, we will make the hundreds of kgs at a place where it's translatable to a commercial scale production facility, using your equipment, using your techniques, showing that it is scalable. To this point, the example on this slide is a facility that we opened up in the fall. It's called the Low Enriched Fuel Fabrication Facility. What this really is a radiological facility with an authorization basis for working up to HALEU-type materials, where we can pilot scale production materials that are of use in novel reactors. The first set of experiments in this facility is tracking to be the fuel for the Hermes reactor that Kairos is looking to put in Tennessee. And this is that pilot scale production capability that then can track to that broader scale production lot at a commercial plant. Transitioning to the second part of the strategy, which is really how do we design to manufacture, I want to talk a little bit about our NRCg facility. This is a facility we operate at the Nevada test site in partnership with the Nevada test site. And NRCg stands for the National Critical Experiments Research Center. And I saw a picture of this facility and experiment on a previous slide, but with no attribution to where it actually sits. I want to make sure that folks know that this sits at Nevada, although experiments within the facility are conducted by Los Alamos. This is a facility that is designed to do criticality experiments, with over 1,000 criticality experiments under its belt. Recent investments in that facility have allowed us to look at criticality experiments on helium materials, and those have been advertised in publications such as these shown here, and have really been important to national security implications and global security with regard to safeguards, but are now translatable to that prototype, that design to manufacture type of problem. So 2.5 years ago, folks at Los Alamos were asked, what would it look like to design a transportable microreactor with materials that are readily available? In 2.5 years, we went from that question to a design that we're inserting in the NRCg facility and taking critical this month that addresses just that, with the UO2 fuel basis and a design that we believe is scalable to be transportable. That concept is called the ZeaCore reactor. This is the exact kind of capability that we're building at the DOE labs, is going that fast. The capability itself is not just for Los Alamos. Clearly, Livermore and our other partners within the DOE complex are using the NRCg capability. However, recently, and as early as this fall, we were instructed by DOE to entertain the insertion of industry-led experiments at the NRCg facility. In October, we were alongside DOE-NE, a company called Valar contacted us to do an experiment as quickly as December of 2025. So the call came in October of 2025. Criticality experiment was inserted in the NRCg facility in December of 2025, and while the initial tasking was to do 5 criticality experiments, we did 12. Since then, we've had 2 other companies in the NRCg facility obtaining data. These facilities were zero power tests. However, the facility itself does have the ability to do power tests. That will have to be something that is adjudicated with NNSA. Next slide. Oh. Final slide. And I think I'm officially out of time, but the point that I wanted to make is the point that I made at the beginning. We have these capabilities. They don't just exist at Los Alamos. They're broad spread across the complex, and we are ready to help. We want to be part of this. We want to be part of the solution set. It's not always obvious to us where we can be part of the solution set, but we're eager to have those dialogues. Thank you.
So good morning, and I appreciate the opportunity to be here to broaden the horizon a little bit more than the U.S. activities and talk more about international research to support innovation. And so I'm here today to talk to you about the Nuclear Energy Agency and what we are doing to enable innovative technologies for regulatory applications, focusing on nuclear safety research. So, many of you may not be familiar with the NEA. Here's just a background slide. We're founded in 1958. There's 34 member countries. We have 74 working groups that work on a range of technical and policy and legal issues related to nuclear power. And we have 20 ongoing international joint projects. In the life of the NEA, there's been about 80. 60 of them have been completed and 20 are ongoing. And our mission is, it's a forum for cooperation on nuclear safety and development for the most advanced countries in the world. We also work with embarking countries to support their development activities as well. Just as background, the two main committees that I'm familiar with are the Committee on Nuclear Regulatory Activities. As it sounds, it's focused on regulatory activities. And then the Committee on the Safety of Nuclear Installations, and that's the committee that does most of the basic research. We heard from Raj this morning about research and the importance of research to enable the safe use of advanced technologies. So we started with research, and I'll end with research in my talk. We heard from Ellen about the national capabilities at the DOE National Labs. NEA works with the national labs. We also have access to a broader international research community. And some of that work is done under, like I mentioned, the 20 joint projects that we have. It includes NEA member and non-NEA member countries, and they do nuclear safety research and collect experimental data. We maintain nuclear safety databases. We do basic science on thermal hydraulics, for example, on advanced fuels. We look at radioactive waste management, radiological protection, and we've started looking at regulatory approaches and processes, security, licensing process, and most recently on disruptive, innovative, and emerging technologies. In addition to the joint projects, we also do international initiatives such as Generation 4 International Forum that looks at sustainability, economic safety, reliability, proliferation resistance, and physical protection. The multinational design evaluation program that's coming up on 20 years of existence here shortly. And the goal of the MDEP is to leverage their resources and knowledge to look at new reactor technology designs. And also the International Framework for Nuclear Energy Cooperation, or IFNAC, and it's looking at supporting developed and emerging economies. So I'm going to shift to our joint projects, and the joint projects are cooperative activities, and it really looks at conducting the research that undergirds innovation. Under the NEA joint projects, research is conducted that has supported adoptions of technological advancements since inception, and is working to support innovation for new and advanced reactors. Why do we do this? We want to understand the phenomenon that affects safety. What's the data that we can collect that undergirds the modeling and simulation that's done to assess the validity of design and looks at design assumptions. We share resources. Research is financially and staffing. There's a lot of resources that go into making that happen. So rather than doing it independently, let's do it collaboratively. So we work together and share worldwide expertise. And it also helps to maintain key research facilities and competencies. And like I said, facilitate cooperation between countries. As an outcome of this, we obtain high quality data for safety code validation and benchmarking safety codes. So when you're looking at designing a new plant, if it's a light water reactor, we have a tremendous amount of data on that. And I'll touch later on some other work that we're doing that's advancing into non-light water reactors. But to validate your codes and models, we have a tremendous amount of data. And we heard a lot today about innovative technologies for improved operational efficiencies, design reviews, and licensing. And similar in the design process, data is critical. So when you're looking at developing a new technology, you're looking at modeling that technology, you're looking at simulating that technology, the data that undergirds that is critical to ensure that your codes, your models, your simulations accurately reflect the real world. So the NEA's goal for joint projects is to advance nuclear safety and accelerate consensus on key safety challenges through shared expertise and cost-effective research. You can't do this without understanding the priorities and the needs of the industry you serve. So the NEA developed a strategic roadmap for nuclear reactor safety research. The aim is to guide international research activity by identifying priorities and strategic directions. It's focused on reactor safety, and it presents a comprehensive assessment of the current technologies, research infrastructure needs, stakeholder engagement, and the funding challenges faced by research organizations. It highlights the most urgent technical areas and provides actionable recommendations to support prioritized safety research. And it can also be used to align research initiatives with the safe acceleration of nuclear deployment. The areas that the safety research roadmap touches on are thermal hydraulics and containment, severe accident, fuel performance and safety, material integrity, multi-unit operations, and nuclear security. I'm not going to go into the detail, but we touch a lot of areas. We collect a lot of data. So the roadmap provides a strategic pathway for globally aligning research. And it involves the NEA, regulators, vendors, technical support organizations, the industry, designers, academia, and other research organizations. I'm going to touch a little bit on one of the joint projects. It's NEA Athena, and it's a global platform for nuclear thermal hydraulic safety research. Currently, it's focused on water-cooled reactors, but it's looking at also SMRs and advanced reactor designs. The goal is to sustain facilities, validate codes, and share data. It's also a platform to support training, data preservation, and looking at developing new applications. And the impact is that it will result in safe, efficient, innovative nuclear expansion. Athena, the priorities and technical focus. The initial focus, as I mentioned, was on water-cooled reactors. The main technical domains were core thermal hydraulic phenomenon, reactor coolant system behavior and performance, coupled reactor coolant system and containment interactions, innovative components and compact systems, and then cross-cutting issues. The cross-cutting issues include multi-physics coupling, fluid structure interactions, and flow-induced vibrations, the active or passive systems interactions, for low pressure and gravity driven systems, hydrogen combustion and thermal stratification, and then looking at spent fuel pool thermal hydraulics. Strategic collaborations, while we have the joint projects, I mentioned the working groups that we have. We have a working group on accident W-Gamma. I'm sorry, I lost the acronym. But they look at severe accidents and accident progression. We also develop international standards problems and do benchmarking and also data preservation. And we are supporting the development of artificial intelligence and machine learning ready data sets. And looking to the future, we are hoping to use innovative modeling tools and methods such as AI and machine learning to improve research activities. So Athena is moving into addressing advanced reactors and SMRs. We have been doing work that looks at passive systems, modeling innovations in computational fluid dynamics, severe accident management countermeasures, advanced measurement methods and instrumentation, and modeling robustness of thermal, hydraulic, and severe accident safety analysis codes. To support the development of models, codes, and methods, the NEA maintains, it's called the CS&I Code Validation Matrix. CS&I is the Committee on Safety of Nuclear Installation. And the CCVM provides experimental data sets for validating safety codes. And we are in the process of updating and expanding the CCVMs for new reactor types, advanced light water reactors, pressurized heavy water reactors, SMRs, and we will be moving into non-light water reactors in the future. And what the CCVM represents, it's a consensus position or consensus developed matrices that constitutes a commonly recognized set of data for code validation. In my closing comments, nuclear safety research requires wide support from across the nuclear sector to enable the deployment of new advanced and small modular reactors. Promising new technologies require maintaining existing facilities and accelerating the development of research programs and expertise. And the NEA, my last thought is the NEA has created a framework to encourage wider international collaboration to efficiently meet the stakeholders' safety research needs. And with that, I thank you for your attention.
All right, everybody. Thank you so much for our presenters today. You guys are really a group of overachievers because it's like the last day of class before spring break, right? And you're still here, and I wasn't sure if we were going to have questions or if I needed to plant some questions, but there are a ton of questions. So we're just going to go through a few of the questions. I don't think we're going to have time to get through everything by 12:15. However, I'm willing to stay, and if the panelists are willing to give us a little bit of time, are you guys willing? Then you guys could come up and talk to us. We have a bunch of questions here. There was one question, we actually got a bunch of questions about 5069, and so I actually wanted to talk about that very quickly before we hand it over to the panel. But we got several questions around the use of 5069 and the risk categorization of our structure systems and components and why that's not used more, why that's not mandated as an approach. And I just wanted to share with you, I think that the theme in the question was really, why aren't we forcing everybody to use that? Why isn't everybody using that? So I just wanted to give a quick history lesson for those who might not be aware. So when 5069 was first identified, right, as a new rule for us, we really were operating under the confines of a more deterministic and prescriptive framework of Part 50. Why I wanted to share this is at the time, it was really looked at as an option for regulatory relief from the more expected traditional approach. But why it's really important at this moment in time to talk about it is that we wanted to acknowledge at that time, right, that not all utilities maybe had established PRA programs. There was things related to seismic and seismic issues, things related to shutdown modes that not every facility had maturity around. But now, you guys have probably been hearing throughout this conference that there's a lot of work that's been done both in EO 14300 rulemakings and new frameworks that we are introducing. So the construct in the theme around, hey, why aren't we embedding more risk-informed decision-making early on as opposed to, trying to decouple and change existing regulations? Hopefully you'll see that that is actually part of why we move forward with some of these additional frameworks that are going to be out for public comment here soon. So I just wanted to address that because there are some comments. We recognize that. I think the industry is recognizing the value in using a more risk-informed approach for looking at our SSCs, and we hope that you also see that in the theme in the future rules that are coming. So moving on from that one, some of these other ones are higher level questions, but let me first ask for the people in the audience, since you guys are the A+ students who are here, could you maybe, by a show of hands really quickly, raise your hand if you've ever heard the phrase, we just need a little more data in a meeting about enabling technology. So if you sat in a meeting and that was like the question. Okay, so it looks like almost everybody raised their hand. So I guess based on that, the real enabling technology is more data, that we need more data. But with that perspective for the panel, one of the questions we had is how are you guys looking at measuring return on investment associated with the use of AI or any other tool within your organization? Taylor?
Yeah, I can speak to that. So there's a public document out there that Idaho National Lab sponsored with their light water reactor program, where they went out and did some analysis on some of our use cases of how we're using AI. And what it found is it was comparative to all the industry research. So if you go out there and do if you use these applications, and I'm not speaking to the advanced stuff that I talked to, but it's actually in that deal, every time you use it, and I'm sure everyone in here has started using it at some point, that there's a base of 30% efficiencies in almost all your tasks. It can go to the hundreds of percent, finding documents that are deep or drafting. So there's a public document out there that goes into quite detail on that, and we measure that. I'll go into another detail. It's not really about, and it goes in the commercial market, it's not about the reduction of staff. It's what else can they do that they didn't have time to do again? Can they do the walk downs? Can they go do the things that they just didn't have time to do because the administrative load that now this can assist with?
Sorry, didn't know you had to hold it. Yeah, I want to talk about return on investment. At Southern Nuclear, to give you an idea of some of the return on our investment, and some of it's not tangible, but some of the tangible return on investment is the number of our co-pilot agent users, which went up, co-pilot adoption, which went up from about 200 people to almost 1,000 people in 2025 alone. We measure that because if you measure what matters, you're going to get to see what your return on investment is. And we saved approximately 2,600 productivity hours for our employees. In our use of the tools around maintenance rule and work orders and corrective action program, we saved about 4,000 man hours of our engineers' work. So I really do think that there is a tangible return on investment if people are willing to use the tools. And imagine the more use, the more return on investment you're going to get.
Thanks, Cheryl. Go ahead, Taylor.
I got one fun fact for that. So we rolled out to our fleet our chat bots and our internal AI. We rolled out to the fleet in July of last year, and we're over 50,000 uses today. And we trend that. So we trend who the users are. So that's over 600 people within our nuclear fleet and trending up. So if it is not a good tool, it does not get used. And the proof is we are getting efficiencies, and we track it through those metrics and the metadata.
Thanks, Taylor. I'll just add, within NRC, right, we're also embarking on our AI journey, and we've been very deliberate around use cases on how we can identify the benefit of the AI and how we can measure that. So I don't know if you had an opportunity to sit in on some of the sessions earlier in the week, but if not, once they're up in web streaming, it would be good for you to take a look. But we have some areas where we've already implemented the use. And the same themes that you heard from Cheryl and Taylor, we're seeing at NRC too. So we're having to identify those areas, look at hours reductions in terms of those initial first drafts. But one of the things we do really want to emphasize, especially for folks who are reluctant to lean into the use, is that it's not resulting necessarily in that there's less people. Could there be less people in certain areas? Absolutely. But also, how do we redirect the attention of the people, right? Rather than working on, writing emails or writing first drafts of things, like how are we really being able to focus their attention on the more critical issues? So thanks for that. So we have another question here around what barrier would be something that you would look at needing to solve in terms of deploying enabling technologies in nuclear, whether it be more data, more demonstrations, more regulatory clarity, more funding, maybe all of the above. From our panelists' perspective, as you sit across, international, the labs, industry, what do you see as the biggest barrier?
So I think I touched on that, and I think other members on the panel touched on that. I think it's really data. You've heard it, data, data, data. That's what you're hearing. But it's not just raw data. It's got to be curated. It's got to be usable. It's got to be in a form that can be easily used by your AI, your new tools, understandable. So that to me is the biggest barrier.
Just like someday I'll learn how to unmute myself on Teams. I'll figure it out here. I think data is incredibly important. It's actually my job to generate data and be the person who feeds the AI beast. But I think one thing I would urge the community to think about that is sort of entering my thought process more and more is a parsing of what you're actually trying to do. It's not going to be a one-size-fits-all strategy. There are going to be technologies you want to insert immediately, and the tools you're going to use for that are going to be really different than the technologies that you're in for the long haul and you're not inserting in the next 2 years. And you're going to use really different sets of tools for that. Additionally, as you consider the use of AI, there's sort of the AI that we're all using, the AI that my son is using to write his paper that he shouldn't be using, right? And then there's the AI that is really going to transform what we do. The use of AI for uncertainty quantification and things like that. And a first step, I don't want to put down the stuff that like my son is doing right now. I really don't, because that's part of an AI-ready workforce. But we need to get to the serious conversations of where AI can solve the problems that we can't solve right now. And what are those problems, and where do we need to make AI work for us, not where is it already working?
I'm going to give a very direct to that of barriers, legal. So the best advice I could give you for implementing is get legal counsel hired that understands AI, that can really look at the risk, and you will make a lot more headway. That's probably the one advice I would throw out there, the barrier that we broke down, because when they don't understand it, they fail safe.
So I'll bid on, there's two questions that sort of build on what you talked about, and so I'll ask them both and then you could answer. So one was related to, and Ellen touched on this, the ready workforce. So even though her son is using AI to generate his papers, my son is probably doing the same. That is important, right? Because that's part of user adoption to get people more comfortable in using those tools. But in addition to that, what is something that you would give as advice to help people be ready for the future workforce? And then two, to Taylor's point on the legal risks or the risks associated with the use, how do you see maybe AI being used to help us identify the unknown unknowns?
Yeah, I can start with that. Well, I think it's kind of cool that your sons are using the AI for their papers. Maybe their teachers don't, but but that's our future. That really is our future, because even, this is our future and that's their future. So, I think we have to move with that future, because it is going to continue, and the future of folks sitting up at this table here in 10 years are going to be very different than us and what they use. So, it's kind of a counter to do it for your homework, but it is our future, and we have to figure out how to make us do that future sooner.
Yeah, and I'll just share, my daughter might be even worse than my son. So, this is like the Snapchat generation and everything. And I was sharing with somebody, her number one friend on the Snapchat is this person named Kevin, right? And I'm like, who is Kevin? Like, who are you talking? And it's her bot. It's her bot that she talks to. I'm like, this is kind of alarming, but here we are. Okay, let me ask you, we probably have time for just one final question. So if we as we wrap up, I think all of us have worked on some project along the way where around the room, around the table, everyone was like, this is the revolutionary thing, right? But 10 years later or 20 years later, we're still talking about the revolutionary thing, and it's sort of making us wonder, how revolutionary is it? But let's say, we fast forward 10 years from now and we look back and we say, hey, this was really the era where enabling technologies were accelerated, or there was some breakthrough that really fundamentally changed the way we work. How would you say, if you reflect back on it, how would you say what would you say are the biggest enablements or the biggest things that helped us deploy the new technology, whether it be a breakthrough in our approach of thinking, whether it be a type of technology itself? What do you think will have made the biggest difference?
I think there's a couple things that we all talk about, and we use this word a lot, but risk, because you can use this to identify risk and back it up quickly and make better decisions. That's when we all know the guy that you would invite in there because he kind of knew the whole picture. And that's exactly that, because you can go in there and it can identify risks and make those decisions. And once those quality decisions come up, nobody doesn't want that again. Have you asked it? Did you go ask Bob about this? Like, he really knows about this, right? So that's exactly where this is you can go through, has this ever happened before? What was the outcome? And get that stuff. And we all get dependent on it. Now we don't want to do without it. Because of, now we have the risk of, maybe, have we looked at all the data yet? And now we can. So that's the addictive part in the answers that we all want to do in our day job.
Raj?
Oh, sorry. No, I just wanted to add, I think if I had a similar sentence, I deleted it because she told me she had this question. So I would say that years from now, if you reflect on this moment and say we didn't realize the advancement that we wanted and the urgency that we had, now we understand. Now, if we have not done that, it's because that we had not changed our mindset. It's because of the fear that clouded us. It's because of the fear of lack of data. I keep hearing lack of data. Lack of data is something to consider, but we have the backing of science. We have the backing of expert knowledge. We have developed structures when we don't have a lot of seismic data. We have put them in seismic zones, and we know how to do many things. I think we have not given us a lot of credit. That's what I will think if we did not advance. But if we did advance, I think we have changed our mindset.
Thank you, Raj. Ellen?
And maybe on that lack of data is something that we say all the time. And in fact, when we do something where we generate more data, we think, okay, well now, we'll do less experiments. No, we just generate more data, right? And so I think maybe if I were pushing AI in a direction that, beyond the way that many of us who are learning how to use it are using it right now, is when are we going to get the tools in AI that allow us to deal with the sparse data sets? Because it's going to be part of the vernacular for us, is there'll never be enough in life. You will never have enough data. And so when are we going to get the tools that actually give us confidence in these sparse data sets? And how are we driving those questions to be answered?
Thanks, Ellen. Do you want to add anything?
So just to build on that, we do have sparse data, but I think the challenge that we're facing today, that I think 10 years from now, I'll look back and go, these tools helped us bridge the gap. There's data. We've collected data on so many different technologies related to nuclear power. We've done sodium cooled. We've done tremendous amount of work on, but where's the data? Do we have access to it? Can we verify it? Do we really know where our gaps are? And I think that's, when looking back, that's what I would say is it helped us find the gaps, and it targeted our research where it needed to be targeted, and it gave us the tools to enable this technology.
Yeah, and thank you for that, John. We actually had the session I referred to that we had earlier in the week. One of the things that we always talk about as we go out and talk about AI adoption across the agency is really thinking about the fact that the AI that we're using today is the worst that it's ever going to be, because it's really just going to improve from here. So let me just wrap this up since we are over time here. I just wanted to thank our panelists again for sharing your insights and the incredible work you're doing to advance nuclear innovation. And also thank you for being here on the last day in the rain and asking a ton of questions. We'll stay up here if you have anything further you want to talk to us about. The future of nuclear isn't just about new reactors, as you see. It's about technologies, data, tools, and collaborations that will make it safer, smarter, and more reliable. If today's discussion showed us anything, it's that work happens across industry, government, national laboratories, and the international community, and that's laying the foundation for our future. So thanks again for being with us today. If you would, join me in giving our panelists a round of applause. And real quick, before you head out, just a quick reminder, if you're interested in continuing this conversation with us, we actually have an AI symposium at our headquarters building, which is across the street in the auditorium at 1 o'clock today. So thank you.